again. In the previous video lessons, you learned to write electron configuration of an atom using the build-up principle and Pauli's exclusion principle. Now, in this video lesson, I am going to talk about something called the orbital diagram. Now, what is an orbital diagram? Now, it's another way to represent electron configuration of an atom. And in this kind of diagram, you can actually see how electrons occupy the orbitals of a given subshell. Now, how do you represent these orbitals? Now, the atomic orbitals can be represented in the form of a circle or as a square. All right. Now, the next thing you have to do is to label these orbitals using the subshell notation. For example, if this circle represents a 2s orbital, you need to represent this as 2s. All right. Now, let's say if you want to draw 2p orbital. Remember, a p orbital has 3 orientations. So, meaning you need to draw 3 circles and you have to label this whole group of orbitals as 2p. All right. Now, the last thing to do would be to fill these orbitals with electrons. And how do we do that? Now, you need to show electrons as arrows. Now, remember, an electron can have 2 kinds of spin. Now, if it has a spin-up configuration, meaning that the spin quantum number equals to plus half, then the arrow is going to point upwards. On the other hand, if it has a spin-down configuration, meaning that the spin quantum number is minus half, then the arrow is going to point downwards. Now, before you start putting in electrons in these atomic orbitals, we need to go over one last rule, and this is called the Hund's rule. Now, what does this rule say? It says that if you want to represent an atom in its lowest energy configuration, you need to put a single electron in the atomic orbitals of a given subshell with the same spin before you pair them up. Sounds complicated? Well, let's take the example of when you're riding a bus. Now, it's a natural human tendency that we like to occupy a seat entirely by ourselves. Now, if another passenger comes in and he finds that there's no other seat that he can occupy entirely by himself or herself, he has no choice but to share it with the fellow traveler. Now, the same logic applies in case of electrons. So, let's say we have to put in 3 electrons in the 2p orbital. Now, based on the Hund's rule, you need to put a single electron in each of the 2p orbitals and they need to have the same spin. Now, imagine there's a 4th electron coming in. Now, this 4th electron will see that it has no room that it can occupy entirely by itself. So, it has to share it with one of these electrons. And when it does share it, it needs to have an opposite spin. And this follows from Pauli's exclusion principle that no 2 electrons in an atom can have the same set of 4 quantum numbers. So, do note that when you pairing up an electron in an atomic orbital, they need to have opposite spins. Now, let's go over a few examples. Let's draw the orbital diagram for nitrogen. Now, nitrogen has an atomic number equal to 7. Based on what you have learned previously, the electron configuration for nitrogen is 1s2, 2s2, 2p3. Now, let's draw the orbital diagram. Now, the first thing to do would be to draw the atomic orbitals. You can use squares or circles to represent these orbitals. Well, I like to do it as squares. So, let's draw the 1s orbital. Make sure to label it as 1s. And then we have the 2s orbital. So, again, label it as 2s. And now, let's draw the 2p orbitals. Now, remember, a p orbital has 3 orientations. So, you are going to be drawing 3 squares and we are going to label this whole set as 2p. So now let's do the final job, which is to fill these orbitals with electrons. Now the 1s orbital has 2 electrons. So you're going to be filling in 2 electrons in the 1s orbital. But remember, when you do so, make sure the electrons have opposite spins. Now let's move over to 2s orbital. Now 2s orbital also has 2 electrons. So you will be drawing 2 electrons with opposite spins. And now we have the 2p orbital. And this 2p orbital has 3 electrons. So based on Hund's rule, you need to put single electron in each one of these orbitals, and they need to have same or parallel spins. So this is going to be the orbital diagram for nitrogen. Now let's do for oxygen. Now oxygen has an atomic number equals to 8, meaning it has 1 electron more than nitrogen. So the electron configuration will be 1s2, 2p, 4. So that means there has to be a 4th electron that needs to go in the 2p orbital. Now based on Hund's rule, each of these orbitals already have 1 electron each with the same spin. So the 4th electron will have no choice but to share its room with one of these electrons, and when it does so, it needs to have an opposite spin. So this is going to be the orbital diagram for oxygen. Now let's look at one last example. This time we will be drawing the orbital diagram for nickel. Now nickel has an atomic number equal to 28, which makes it a bit more complicated. So let's write down the electron configuration for nickel, which is 1s2, 2s2, 2p6, 3s2, 3p6. Now remember, before the electrons occupy the 3d orbital, they first occupy the 4s subshell. So you will be having 2 electrons occupying the 4s orbital, and the remaining 8 electrons will occupy the d orbital. So now, since we already have pictures for 1s, 2s, 2p, we need to draw orbitals for 3s, 3p, 4s and 3d. So let's do that. So after 2p, we are going to be drawing the 3s orbital and label it as 3s. Next, we will be drawing the 3p orbital again, which has 3 orientations, and you are going to label this as 3p. And then you have the 4s orbital, so you are going to label it as 4s. And finally, we are going to draw the d orbital. Now the d orbital has 5 orientations, so we are going to be drawing 5 squares. Okay, so let's do that. So it's 1, 2, 3, 4 and 5, and we are going to label this as 3d. Alright, so now let's fill in the electrons. So 1s has 2 electrons, so let's put 2 electrons of opposite spin in the 1s. Then let's do for 2s, and let's put 2 electrons in the 2s orbitals. Now p orbital can accommodate maximum of 6 electrons. So we have to put in 6 electrons in the 2p subshell before we fill in the 3s. So let's put 1 electron in each of the p orbitals with same spin, and then we put the remaining 3 with opposite spins, and they have to share the room with another electron. So now let's move on to 3s. So 3s has 2 electrons, so let's put 2 electrons in the 3s orbital, and again the 3p orbital has 6 electrons. So let's start by putting 1 electron in each of these p orbitals, and then the remaining 3 will have to share the space with another electron, but they need to have opposite spins. Now let's move on to the 4s. So 4s has 2 electrons, so let's put them here. And now finally we have the 8 electrons which will occupy the d orbital. So, again based on Hund's rule, let us put one electron in each of the orbital of the 3D subshell. Okay, so we have 1, 2, 3, 4, 5. So, there are 3 more electrons that need to occupy the 3D orbital, and they have no choice but to share the room with other electrons, and they need to have opposite spins. So, now we have 1, 2, 3, 4, 5, 6, 7, 8. So, this is the orbital diagram for nickel. And that brings us to the end of this lesson. We will be doing problem solving in the next video. Thank you.